Hello. So today we are covering a review about compressive optical steganography via single pixel imaging, which is done by myself, that is Manthan Jani, and my colleague Dhruv Gajjar. And this is carried out by some experts that have been mentioned in the slide. So this research is based on a compressive optical steganography based on SPI, which is basically the single pixel imaging. And what it does is that it just employs a digital light projector to illuminate the host image with modulated patterns in it. And it is similar to a wireless broadcast system. So it is used in the compressive sensing technique, and an algorithm is applied, which is a generalized phase retrieval algorithm, in which the secret message, which has to be encoded within the host image, is parse sampled or compressed and then encoded via the illuminating patterns, which are then projected onto the host image in an single pixel imaging architecture. So the resulted reflecting light signal travels in free space uh, and can be authenticated by anyone, but it cannot be accessed by anyone because it has the uh, a series of keys which are not available to the eavesdropper or the attackers. And by implementing the inverse Fourier transform, we get the stego image or the hidden image or the modified image and can be received as the host image. However, only authorized receivers who possesses the secret key, which is the RIM key, could extract the desired data from the Stigo image and then reconstruct the secret message by using the convex optimization algorithm. Because this algorithm is the most promisable one, and the secret message is then sparse sampled or compressed before embedding, uh, which uh, which helps in the imperceptibility is well preserved while the capacity also is kept in a high level. So as we can see, this is the apparatus of the real-time based application. So first, what it is done, the secret message is Fourier transform, and it is been sent to the digital light projector, which with then combines with it modulated wave patterns and represent it on the host image. After that, as I explained earlier, it is a wireless broadcast system. It can be authorized by anyone, but the receiver who possesses the RIM key will be able to authorize it, and after that it will be uh, received by the bucket detector, in which the stego image will be formed in an analog pattern, and then the extraction will be carried out using the correct key, which is the RIM key, into the digital uh, signal. Now I would like my colleague Drew to take it over from here.
So, hello there, everyone. My name is Gajjar. So, let's introduce the topic and concepts of steganography. Basically, steganography is the practice of hiding message, data, image, especially image, into another object, right, with minor changes in object, which will result into stagnated object, or you can say a minor change in the original object, which has a hidden message in it, and human senses like visual, audios cannot differentiate between. There are various digital steganographic methods proposed throughout this decades, especially in spatial domain and uh, frequency domain, right? In last 2 decades, single pixel imaging scheme technique shows great promise. Capture with multidimensional and multispatial, multispectral information by using single bucket detector, which can detect a single pixel without spatial resolution. A SPI consists of a light emitter with one or more receiver. It works like a wireless broadcast system. Anyone can detect it, but only authorized user can decrypt it. By employing the broadcast like single pixel imaging technique, we design a covert communication that is known as secret communication system, which regards as optical steganographic scheme. So basically, steganography, the communication capacity and interceptability are two contradictory attributes. Like, if the capacity of the secret image or secret message increases, the interceptability also increases. It's There are better chance to intercept that this is an stagno image, it's not real, and it has an hidden message in it, right? So remedy this issue, basically compressive sensing, or we will compress our secret message into any object. Our review is based on optical steganography. So we'll talk about this research. Basically, they have proposed an compressive optical steganography to compress the secret message and embed it into an host image, and we will retrieve that image nearly perfect through convex optimization algorithm if you know all the key control parameters or random index mapping, which I'll be showing you. So So as you can see, there is a physical host image. There is a digital light projector DLP and single pixel image. And this whole architecture is of single pixel imaging architecture. There is anyone can detect this stegno image. Uh, Anyone can detect the stegno image because it's absolutely openly broadcasted through bucket detector, but only the authorized person or the person who has RIM with him can decrypt the secret message. So as shown from the previous image, there's a digital light projector which will be emitting modulated light patterns or Fourier based fringes on the host image. The host image is a physical image, and then the light reflected will be broadcasted to everyone. Anyone can detect it, but only authorized person can decrypt it or extract the secret message from the stego image. Apparatus that is being used is bucket detector BD, single pixel imaging, that is SPI, DLP digital light projector, a host image, and a secret image. Now we'll be talking about actual embedding process. That is, we will be uh, we will be compressing its secret image and converting into Fourier transform fringes, and then it will be index mapped and it will be restricted. I will be showing you the figure now, like this. So first there is a secret image, and its Fourier transform will generate a spectrum. We will be restricting the spectrum and converting it to a numerical data by using IM index mapping, and will be generating a subspectrum, or you can say spectrum subset. Uh, and from that spectrum subset, using generalized phase retrieval algorithm, we will be converting it into modulated wave pattern. Then that modulated wave pattern will be randomly index mapped and will be projected on host image to generate the stegno image. Now, retrieval process is opposite of it. So by using stegno image, we can we have to decrypt by using random index mapping. That's our key. So from the stego image, if we have RIM, we can decrypt the secret image spectrum subset, and using convex optimization, uh, we can generate the secret image through extraction.
Hello, I'm Manthan again, and I'd be taking it from here. As my friend explained, this is the transformed spectrum, that is the Fourier transform spectrum image of the original image. And what we are going to do basically is we are going to uh, represent it on the host image, and that's how it looks like in the real time. So as you can see this graph, this is the visualization of time domain frequency domain measurement. The image basically is a 2D signal, and it can be visualized from two different domains. The first one is the time domain measurement, and the second one is the frequency domain measurements. With regards to the time domain measurement, we can see that uh, the the green wave is the addition uh, of the three frequency waves, which can be visualized as a single one. And from the frequency domain perspective, all the three waves which are visualized in the frequency differently. So basically, our research is on the frequency domain measurements, and we are going to carry out this. So what happens in the block diagram is that the host image and the modulated wave pattern are Fourier transformed to impose Fourier constraints, and as a result, we get H m dash k, which is nothing but basically an image, and it is for the inverse Fourier transform to get the particular value. Uh, Here, what happens is that the spectrum domain is converted back into the signal domain, and this repeats to the kth time in the equation. So, blocking. Uh, so here are the three steps which I explained in the earlier diagram, and after that, it's the formula to find the k plus one iteration of the modulated wave pattern. Here, TPS is just a constant, and it is the minimum constant for avoiding the division by zero error.
So I'll be taking it from here. Uh, so now we'll be talking about extraction process that is happening. So as I said and mentioned earlier, the one who has random index map, that is our key, then that can only be extracting the secret image. So we have to construct the measurement matrix according to the index mapping that we have recovered the secret image. By utilizing y and phi, we can reconstruct the secret image x as following equation. Now there is a problem in extraction process. Why? So basically phi is a matrix of 10,530 cross 32,400, and it has more column than x. So if we want to retrieve x by using y and phi, it's impossible. So we will be using CS method or compressed sensing method to find exact or appropriate solution for the undetermined linear system of equations. So here shown some statistical analysis formulas, that is CC, correlation coefficient between the two images. We will be finding correlation coefficient between Saginaw image and our host image. Our secret image, that is, it is been embedded into the host image, and the one image, the secret message that we have been extracting it.
So here, basically, they have performed the simulation results in the MATLAB. So the first image that is been labeled as A is the host image. The the image labeled as B is the secret image, which has to be superimposed in the host image. The image C is the combination of the first and the second image, that is the stego image, and the image D is the extracted image, or the image that has been uh, received back. So we can see that the correlation coefficient, which my friend explained further, was is 0.9776 between the A and the C image, which is the host, and the uh, stego image, and the correlation coefficient between the secret image and the extracted image is 0.9956. So this is the graph which can be shown. So what happens basically is the CC, it is the graph between CC and the image size, and the CC value between the stego image and host image is represented by the blue line, and the CC value between the extracted images and the secret image is represented by the red line. And as the size of the image increases, we can determine the change in the CC values. So this is the real life project implementation of our result analysis. What happens is the DLP, which is the digital light projector, superimposes the modulated wave pattern on the host image, which is then detected by the bucket detector in an analog pattern, and the stego image is formed. This stego image is passed to the ADC, which is analog to digital converter, and then it is converted back into the extracted image, and the host image separate, and the quality is affected as well here. So this is the real life result experiment. So results are basically this that are displayed on the screen. Here for the first image is the host image, and the second one is the secret image which is embedded, and the third one C is the stego image. We can see that there is a slight blurred image, but it is the stego image, so B is embedded within it. And when it is extracted, we can see some noise in the secret image, but it is very well for communication.
So as my friend Manthan mentioned earlier, there will be a factor of noise would be affected. Let's talk about it. So this is SNR. So SNR is signal to noise ratio. So when noise increases, the quality of image decreases. So correlation coefficient also decreases with respect to 2. So as the distance increases, noise increases. So quality will degrade it accordingly. So let's conclude this. This experiment basically displays optical steganography using single pixel imaging scheme by generating index map and by compressing it and making sparse sampled Fourier matrix, that is phi, which is used as in measurement matrix, and the embedding process is done by generalized phase retrieval algorithm to illuminate the pattern on the host image. We'll use single pixel imaging system. For extraction, we need RIM, random index map, which we have done. If we have a correct key, then we can extract the spectrum subset. And later that spectrum subset could convert using op- optimization, convex optimization algorithm to into digital image. So in this experiment, imperceptibility is well preserved while the capacity is also achieved with high levels. So they have introduced compressive sensing theory in this research, and they have constructed nearly perfect image. So these are the references. Thanks and goodbye from Manthan and Dhruv from CHARUSAT University. Thank you.